already have some notes that you've taken for these concepts. You guys probably read something about, I know you read something about, and probably maybe wrote down a few notes about heat and temperature. The one thing that your book doesn't do, and is as exceptional a job of as I would like them to do, is the distinction between heat and temperature. Would anyone like to offer up what they discovered heat to be? What is heat? Zach? It is the amount of, okay, heat is a form of energy. Okay, there's a bunch of different forms. What are some forms of energy that you all are familiar with? Let's call heat one of them. What else? What's that? Kinetic energy, which is the energy of, we need that one, of objects in motion. Great, great, great. What's that? Yeah, and you said potential. I heard a few people say potential. There's a bunch of different types of potential energy. The one that you're familiar with probably most from your earlier science classes was... Does this object have energy as I'm holding it? What type of energy? Which type of potential? Who said it? Who said it? Why did you point to him? Oh, okay. Gravitational potential. So energy of position, right? Since it's above a reference point, the floor, the table, whatever, it doesn't matter, it has gravitational potential energy. What are some other types of potential energy that you might be familiar with? Elastic potential energy. That's good. That one doesn't come up very often. Electric potential energy. So electricity is essentially, did anybody do electricity in physical science?
Yeah.
Some of you did, some of you didn't. Okay. So you guys have heard of voltage before, right? Okay, that is electric potential energy. There's also chemical potential energy. Chemical reactions can have some energy involved with them, and there would be a chemical potential energy. So anyway, there's a bunch of different potential energies. We've already covered electricity. We've covered gravitational potential energy. So anyway, there's a bunch of different forms of energy. There's more, but this is good enough for now. Heat is one of those. So let's be more specific. What is heat? It's thermal energy. That's another way of saying heat. Thermal energy. What is thermal energy? You guys just keep coming up with different names for the same thing.
High temperature.
Okay. As it turns out, heat, energy as heat, is a measure of, are you ready for this? The sum of the kinetic energies of the particles in a sample of matter. Heat is a measure of the sum of the kinetic energies of the particles in a sample of matter. Heat is a measure of the sum of the kinetic energies in the particles in a sample of matter. So essentially what you can do, let's imagine that you all are a sample of matter, and you are all the particles that represent that sample of matter. What we would do is measure the kinetic energy of each and every single one of you, and then add all that up. Now, is that very likely to be done with the particles that make up this sample of matter in here? What is kinetic energy again? Someone said it earlier. Energy of motion. What information is required to find the kinetic energy of any object? Does anyone remember the equation? Okay, well then here's a little demonstration that I like to do. Does this object have kinetic energy?
Yes.
Why? It's moving. What does it have? What properties does it have since it was moving? It has a velocity. What other property does it might have? Well, let's do this. You looked a little bit more nervous.
It looks fragile.
First, looks fragile?
Yeah.
Probably not the word I would have used. You weren't so nervous about that. You are kind of nervous about that. What do you mean it's bigger? More mass. So remember, mass is... Does anyone remember the equation for kinetic energy? Well, we just found out that there were two components. Velocity and... Now watch this. Let's see if anything... You weren't too concerned about this, right? Would you have been concerned then? It's the same mass. It's the same mass. So what's different? The velocity. Okay. So what is the equation? You don't have to write this down. This is something you've played with before. What are the two components? Okay. Mass and velocity. Okay. And how does the kinetic energy change if the mass increases? What happens to the kinetic energy? It increases. Therefore, it's a direct relationship. So mass goes in the numerator. What happens to kinetic energy if the velocity increases? The energy increases. Therefore, it's also in the numerator. It's a direct relationship. You might remember, however, that the velocity is squared. Does anyone remember this now? Now, you may have learned the equation as 1/2 times mv squared. I'm going to get rid of the half because you guys don't like halves, do you? You don't like fractions. So watch this. Is that not the same thing? Right? Get rid of the fraction. Okay. So anyway, so there's the equation. So what we need to do to find the kinetic energy, or the amount of heat in this substance right here, is we have to look at every single little particle, every atom, every molecule, and find its mass and velocity, and then add all that up. What's the likelihood of that happening? It ain't going to happen. Okay? It's not going to happen. So we have to come up with other means by measuring how much heat energy there is actually available there. We're going to get to that here in a second. What about temperature? What is temperature? Yes? There we go. So now we're looking at the average, or the average of the kinetic energies. Okay? So that would be, once again, if you guys were the particles in a sample of matter, we would come up with all your kinetic energies and then take the average of those by adding them all up, heat, and then divide by however many there are. Is that something that's likely to happen? No, because once again, it comes down to finding an average kinetic or the kinetic energy of everything. But I do want you to know there is a distinction. Let me walk you through a couple of analogies and see if this will help you figure out the difference between heat and temperature. Has anyone ever been near a campfire before? Yeah. What do you burn when you're burning a campfire? Wood. Okay. What's the campfire for? To generate some heat, right? Has anyone ever lit a match before? Yes. What are you burning? No, that's what gets the match started. Once the match is started, what is burning? Wood. Right? Same stuff that the campfire is burning. Which one of those flames do you think has the higher temperature? They're going to have exactly the same temperature. Why? They're burning the same thing. However, was it kind of chilly last night? Yeah, most of you guys probably recognize it. So if you had been out camping last night, which would you rather have had near you, the match or the campfire? Why the campfire? There's more of it. So do you see the difference between the average kinetic energy, temperature, and the kinetic energy, the heat, the sum of the kinetic energies? There's more energy available with the campfire because there's more of it. There's greater mass. Just helping make a distinction between the two. Now, the hard part is measuring how much energy there actually is in an object, and that's we don't have a device that does that directly. So what we do, and some of you have this written down in your notes from the other day, we can measure the amount of energy by looking at how its temperature changes. Did anyone write down something relative to that? That heat is can be measured by looking at how an object's temperature changes? Did anyone write anything like that down? Okay, well that's basically what your book says. So I just kind of clarified some of that stuff. Anyway, there is a handy-dandy little equation that we can use that will help us do that. And I'm going to show you that equation now. This is the one that was in the book. This is the one that 8 of you actually wrote down. The rest of you decided not to and couldn't figure out what to do with the problems. Okay. How many of you wrote that down from the other day, Friday?
Is that different?
We're going to go through this. So, what does the Q stand for? You guys didn't. You wrote down the equation, but you really didn't. Heat. And what are we typically going to measure this in, based on what your book told you? And they were pretty accurate. Joules. And you guys remember the joule from your other energy things that you covered back in whenever you took physical science. Anyone want to take a stab as to the M? It is mass. And what are our masses going to be measured in? Grams. Very good. Now, this is where I am going to deviate from what the book. They kind of give you. Did anyone notice they gave you 2 different temperatures to use in this stuff? Did anyone happen to catch that? Okay. Well, in there, let's look at this piece right here. What does the delta T stand for? Go the other way. Flip that. And the initial. Yeah, anytime we have delta, it's always final minus initial. You guys knew that meant change in, I believe, yes? Okay, but it's always final minus initial, and if you do it that way every time, that's going to give you a specific sign. The sign means something. If you remember from your physical science days, your velocities could have a negative velocity or a negative acceleration or a positive, so on and so on. It includes direction. So this is change in temperature. And remember, that's always final minus initial. Okay? Which leaves us, oh, and by the way, what are our temperatures to be measured in? Well, when your book was defining this equation, I believe they told you to use the Kelvin scale. Is that correct? But if you looked at the problems, the example problems that were done a little bit later, you'll notice that when they gave you information regarding the temperature, they would give you something called a heat capacity that was degrees Celsius. So does it matter which scale you're in when you're looking at temperature difference? It turns out no. Does anyone remember how to convert from Celsius to Kelvin? We did that earlier this year. You add 273. I'm going to tell you when we get to the gas law stuff, add 273.2, but you add something. And if you want to go from Kelvin to Celsius, you subtract, okay? Well, if you're looking at temperature difference, it doesn't matter what scale you're in, you're going to get the same difference. Some of you are looking at me going, really? I'll prove that to you. What if we have, 20 degrees Celsius, and we're reducing that to 10 degrees Celsius? What's the temperature change? 10 degrees Celsius. Whoops. Now, if I convert this to Kelvin, what am I going to do? Add 273. So this becomes 293 kelvins. This becomes 283 kelvins. Whoops. What's the difference? 10. It doesn't matter what scale you're in. For this class, because our instruments, our thermometers, and our temperature probes measure in Celsius, we're going to stick with Celsius. So I guess what I'm saying is, if you see something given to you in kelvins, don't get your panties in a bunch. It still works out. And then lastly, the important part here is this C. Did anyone happen to catch what that represented? This is probably the part that caused you the most problems. What is C? It's flat out. There's a lovely, lovely device. I know it's new and it's kind of beyond your guys' capabilities and comfort level at this point. It's called a textbook. Textbook, that's it. Sitting right in front of you that you took notes out of just recently. What does C stand for? I don't know. I really don't. I don't know. You're the ones that wrote it down. 564. I'm actually kidding. It's near there, though. You got it? 531. Oh, 531. That was not awful. Come and be. Oh no, I'm not. There's no way I can squeeze. You're just too fat. Yeah. What is C? What does it represent? Here's what's funny. The answer to the question has been written on the board since about the time we started the whole conversation. Specifically,
It doesn't have a P.
specific heat capacity. Oh, it doesn't have a P. What's the P stand for? Well, then who
The
cares?
book says it has
I understand that, and what does the P stand for? Pressure, at a given pressure, okay? So, and actually if you read a little bit more deeply, I think it also mentions something about at a constant pressure. Did anyone happen to jot that down when you guys were looking through there? Okay. At a given constant pressure. And as long, well, okay. So is everyone clear that right now we have a atmospheric pressure being exerted on us? Yeah, we got this huge column of air. Does anybody know how big the column of air is? Big. 1 mile? What's that? 100 miles? Yeah, we're probably, I think it's a little less than 100 miles, but let's call it 100 miles just for fun, okay? Column of air sitting on top of us, providing this huge amount of pressure on us. You guys feel the pressure? You guys feeling crushed by the pressure? Look at Matt. Why don't you feel crushed by this column of air sitting on top of you? the only thing you've ever known. Ever. Has anyone ever dove like 10 feet underwater before? What do you feel? Do you feel pressure? Yeah. Okay. So what's the difference? Not only do you have all that air sitting on top of you, you now also have all that water sitting on top of you. Okay. You're not used to that. We're used to the air pressure, so we don't know anything any different. Okay. But we got this huge amount of air sitting on top. As long as that atmospheric pressure stays relatively constant, the reason they put the P there is because there's some things you can do with that later in the chapter that we aren't going to cover this year. When you guys take AP chemistry, though, we will cover that, and it will make a difference, which is why you can get away without putting P there. So what does the C stand for? Specific heat, and if you want to have something to remember why it's a C, capacity. And this is the whole point of the conversation we're about to have right now. Every substance, please pay attention to this. And you guys already know, you're already aware of this. You just never thought about it. So we're going to have some conversations about things that you guys have noticed in your lifetimes, but never really thought about why that's true. Every substance has its own unique ability to absorb energy without changing its temperature, or a capacity for absorbing energy without changing temperature. Okay, so now I'm going to give you guys a little bit of an analogy here, and then we're going to talk about real things that you guys have seen before. Huh. One of my beakers is missing. Huh. All right. Well. I'm recording it? Yes. All right. So, what's the difference between these two beakers? Their capacity, their volume. Okay? They have different capacities. You guys following? Okay, let's imagine, and again, this is an analogy, okay, that these are two different substances. One substance has a high capacity for absorbing energy before its temperature changes. Another substance has a very small or low capacity for absorbing energy before its temperature changes. Let's imagine that energy is represented by water. Okay? So what I'm going to do, if you see water outside of the container, that means the energy, the object has reached its capacity to absorb energy. The energy is being passed along to the surroundings. Are you guys following the analogy? So I'm going to add some heat to this. Was it able to absorb the energy? Did its temperature change? Is it able to pass that energy along to the next object? No, because it was able to absorb that. What if I add more? Okay? I'm adding a lot of energy, aren't I? How are we doing here? Is any energy being passed along to the surroundings yet? Nope. I'm going to throw this on him. How about now? Is energy being able to be passed along to the surroundings? Right. But as we saw, it had a very high capacity for absorbing that energy, right? Now I'm going to take the energy in this container, this object, and add it to some of this. And let's see if it has the same capacity. Okay, so do you see where I'm going with this analogy? Okay, this object, yeah, who cares? This is just water. This object is able, it can only absorb a little bit of energy before the extra energy gets passed along to the next part of the surroundings, whatever that happens to be. Okay, so now let's apply that to things that you guys have experienced in real life. Has anyone ever tried to boil water before? Almost all of you have tried to boil water before at home in the kitchen, right? How'd that go? Does it go very quickly? Not very quickly. So let's imagine, what are you guys making? Macaroni and cheese? Ramen noodles? Do you do it? What? Okay, I'm talking about on a stove. Okay, spaghetti. Right, okay. So we're going to make something in which we need to boil some water. What's the first thing you're going to grab? A pot of some sort, okay? What are you going to do with that? Put a bunch of water, then what are you going to do? Why put salt in it?
Oil. Make oil in it. A little bit of oil.
No, it doesn't. We're going to get to that. We will. No, it doesn't. By a long shot. There's so. Listen, I know that's what you were told. Okay, but there are so many things wrong with that statement. We will cover that in a whole separate thing. Okay, later in the year. But anyway, and it's not your fault. It is flat out not your fault. And it's not your parents' fault who told you that. I said it's not your parents' fault. And it's not your grandparents' fault, okay? Because that's been passed along for, yeah. Anyway, we'll get to that later. So you put the pot on the stove, full of water. What do? Turn the stove up to probably high, right? Great. And it boils within seconds. Oh, no, it doesn't, okay? So what do you guys do? Well, you go off and do something else, but being the young adults that you guys are, you get a little impatient, right? You come back. How many of you have, and I can think of 5 right off the top of my head that have done this, how many of you, after like 2 or 3 minutes, have come back and stuck your finger in the water to see if it's hot? Would you like me to pick you out right now? Who's done it? Go ahead. It's okay. It's not like you're in trouble or anything. Who did it? Raise your hands. Great. Did it burn your finger? After 2 or 3 minutes? No. How many of you have done it after 2 or 3 minutes and it didn't burn your finger? Right. Did it feel warm? Maybe a little warm. Now, let me ask you this. At the same time that you stuck your fingers in there, please pay attention. At the same time that you stuck your fingers in there, did you also put your hand on the side of the pot? You did? Why would it make a difference? The water's not hot. The pan heats first. And not only does the hand heat first, it heats faster. No. We're going to come back to that. We are going to come back to that. We're going to change your world here, okay? In terms of the analogy that I just presented, which of these represented the water? Which of these represented the metal?
The beaker.
Metal, water.
Which beaker?
The smaller.
The small beaker represented the metal because it has a low heat capacity to absorb energy before that energy gets passed along to its environment. Now, what's the next part of the environment for the metal? The water that you're trying to heat. Water, on the other hand, has one of the highest heat capacities of substances that are around. Therefore, it has the ability to absorb a very large amount of energy before its temperature starts to change. Does that make any sense? Okay. Metals typically have very low heat capacities. Water has one of the higher heat capacities of all substances. The idea of conductivity ended up coming into play here a little bit by a few students I heard say something. Caroline said something. I know a few others did. What does that mean? You say metal is a conductor. What does that mean?
They produce.
No, they do not produce heat.
Heat produces.
Their heat capacity is so low that additional energy is passed along to the next object, to the next piece of the surroundings. So if something is an insulator, you've heard this word also, right? The opposite of a conductor, that means it has a high heat capacity relative to other things. Nicely done, everyone. We'll pick this up tomorrow.